It is a purpose-built guide to post-construction fatality monitoring in emerging markets. The IFC led this effort, and they intend for this book to define monitoring expectations in emerging markets going forward. So it's an important tool to be aware of. People will kind of expect this to be the standard to which we're carrying out this work. The reading materials, again, that I provided for this lecture include the internet link where you can download this resource. It's also at the bottom of the screen here. So that's something you can put your hands on. The handbook itself covers concepts and principles of monitoring design and includes a decision support tool that will help you design a monitoring study for your own project. It includes practical advice for how to complete the fieldwork, and it has template data sheets that you can use to collect data. Finally, it does include another worked analysis example using GenEst. So onto the objective and the data and the process to analyze. So our objective tonight is to estimate the number of birds or bats that are killed at a wind farm over a specific period of time. And to do that, we send searchers out into the wind farm to count dead things. They look on the ground, they find carcasses, they count them. But those raw carcass counts that they return with are always an underestimate of the number of things that died, because there are some processes that inherently bias those counts. Carcasses are not all detected. So in the next few slides, I'm going to illustrate the reasons that the count is always too low, and that will motivate the way the data look, and in turn that motivates the whole analysis. So this is sort of a conceptual setup for the analysis we're going to do today. So as shown in the cartoon on the left, we have a flock of birds. Some of them may collide with the turbine. We have one that's a red star that has collided, and it will fall to the ground. Now, not all of these carcasses fall in the areas where we search. The carcasses do not fall uniformly around turbines. So the figure at the top right here shows a turbine at the center as a red dot, and all of the little blue dots are around our locations where a carcass may fall. And you can see most of the carcasses fall near the turbine, and fewer of them fall further away. So there's a decreasing density as you move away from the turbine. Now, our budgets are usually limited, so we can't search an enormous area. We search a smaller area. If we search a cleared plot like this, indicated with the hatched square, we're going to have most of our carcasses within that plot, but a few of them will fall beyond the bounds of the plot. On the other hand, if the terrain is very difficult and we can't clear that full plot and we can't search that full plot, we may end up searching just the turbine pad and the access road. That's a much smaller area. You can see we're capturing very few of the carcasses, and a very large number fall outside of the search area. So this bias is simply carcasses that fall where we're not searching. And to adjust for this bias, we estimate the fraction of carcasses that fall within the searched areas. This is called the density weighted proportion of area searched. It's a terrible term. Sometimes we just call it the area correction because it's easier to say. My slides are animated in ways I didn't anticipate. The next process that impacts our carcass counts is the carcass removal process. So we don't have searchers on the ground at all times. They visit the turbines perhaps once or twice a week. And in the interval between when a collision occurs and the carcass reaches the ground and when our searcher arrives, some of those carcasses will be removed by scavengers. Some may be buried by agricultural equipment. In extreme cases, some may be blown or swept away by floods. But for the most part, we think about a removal process as being a scavenger. So on the left, I have a couple of photographs from game cameras. There's a raven consuming a carcass on top, and a fox consuming a carcass on the bottom. These are photographs from wind farms, from experiments that we've done to try and see how long those carcasses last. So this is the carcass removal bias that affects our carcass counts, and we use experimental data to estimate the effect of carcass removal on our counts. Our fourth bias factor is that we typically do not search the entire wind farm. We search a sample of the facility. In the cartoon on the right, I have indicated that we may search just 2 out of the 6 turbines on this wind farm, and obviously any carcasses that fall on the other 3, 4 turbines are not going to be included in our count. So that's another bias that's fairly simple to correct for. Finally, some fraction of the carcasses that survive until our searcher makes it out into the field will simply be missed. These carcasses are often small, they're cryptic, they blend into the landscape, and we don't expect our searchers to see all of them. So that's illustrated on the right here with some carcasses being circled. These are the ones that our searcher has found. The others they didn't find. And what we'll do is use again experimental data to estimate the efficiency of that searcher, and so that we can correct for the carcasses that searcher might miss. So I've listed now 5 components that are involved with collecting post-construction fatality monitoring data. That is the carcass count, the searcher efficiency, the carcass persistence, the sampling fraction at the turbine, what fraction of the turbines we've searched, and the density weighted proportion of area searched, or the area correction. And our entire analysis then can be kind of captured in this one equation, which has all of those components. So in this case, M on the left is the quantity we're after. That's the number of things that died at our wind farm. And M is approximately equal to the carcass count, which I have as C, divided by the detection probability, which is G. Now the detection probability is just what's the probability that a carcass that arrives at your facility will be picked up by a searcher, given all of those other factors that I've mentioned. And that detection probability G, and I've got squiggly equal signs here. This is not an exact equation, but it's a very good approximation to the equation that GenEst uses. The one that GenEst uses is very much more complicated. But this is a good conceptual framework to think about what that software is doing. So G, the detection probability, is equal to, there's our searcher efficiency, that's P. Here's our carcass persistence, that's R. Here's our sampling fraction, that's F. And here's our density weighted proportion of area searched, that's DWP, again, also sometimes called the area correction. And for back of the envelope work, for approximate work, this is good enough to get you to a quick idea. The software will use a better estimating equation, but this is a good way to think about what you're trying to accomplish as you analyze post-construction fatality monitoring data. This carcass count, C, is raw data that come directly out of the field. F is known from the study design, and the other 3 components, the searcher efficiency, carcass persistence, and density weighted proportion, we're going to use statistical estimators to approximate. Before I actually get you into what the data look like, I want to talk about a very important concept, which is analysis strata. So a stratum is just a type or class of carcass. And post-construction fatality monitoring analysis tracks each stratum in the data because different types of carcasses have different detectabilities. It's a lot easier to find an eagle than it is to find a bat. So when we find one eagle, that might represent 2 carcasses that actually occurred. When we find a bat, we might only find 1 bat for every 8 that occurs. So we need to keep track of all of these different strata in the data so that we can get an accurate estimate. Common examples of stratification that occur in the data are carcass size. And we typically recognize 4 carcass sizes. There are bats, small birds, medium birds, and large birds. Carcass size influences detectability. Searchers find large things more easily than they find small things, but carcass size also influences the carcass removal rates. So scavengers are typically more inclined to remove bats than birds, and more inclined to move small birds than large birds. So all of these things are different, and the detection probabilities for those types of carcasses are different. Season is another common stratum. Season can affect searcher efficiency if the vegetation growth is extreme in the summertime. It's simply harder to see things in a highly vegetated area. Season can also affect carcass persistence, as the scavengers are more or less active in different seasons of the year. Finally, plot type and searchability. If we're searching just the turbine road and pad, that's a fairly easy to search plot type. It's a prepared surface. It's typically gravel. It's easy to spot things on it. On the other hand, if we're searching a full cleared plot, there may be easy search conditions within full plots, and there may be difficult search conditions depending on rocks, vegetation, even how difficult it is to walk on the terrain can impact how well our searchers detect things. So these strata are important to keep track of in the study, and importantly, any stratum that impacts detection probability needs to be noted for each and every carcass that you pick up. All right, on to the data. The next couple slides show template data sheets from the Good Practice Handbook that I referenced earlier. And there's usually a lot of information to collect on these. That information is important to collect, but I've highlighted in yellow just those few items that are critical for a GenEst analysis. The other items on these are useful in quality control as you're checking for consistency in your data. They can be important for some of the types of meta-analyses that Tara mentioned in her last talk. But for my talk today, I've highlighted the critical ones. So the first thing we need to know is actually when you searched. Each and every time you visit a turbine and search the plot, we need a record of that event. So on this data sheet, we're going to record the turbine number or some identifier for the turbine, the scheduled search date, and then whether it was or was not searched. Sometimes we're unable to search turbines because there's turbine maintenance going on and it's not safe. Sometimes weather will preclude a search. There may be other reasons it's impossible to search, but we do need to know each time a turbine is supposed to be searched, was it in fact searched? And these data will be collected into a simple matrix with turbine numbers in columns and search dates in rows, and then just a 1 or a 0 indicating whether that turbine was searched. For those of you who are not English speakers, the highlighted words in yellow are reproduced at the bottom of the screen here, and that'll be true on the next couple of slides too. Carcass observations. Each and every carcass gets its own data form. So there's a data form on the left, 1 per carcass. And for each carcass, the critical things that we need are a carcass identification code. That can be a serial number. It can be today's date with a dash and which carcass number it is you found today, number 1, number 2, and so forth. We need to know where it was found, which turbine. We need to know the date of search. We need to know whether that carcass occurred within the delineated search plot. If the carcass fell outside of an area where you're supposed to search, we usually record it, but it doesn't make it into the analysis because our analysis assumes that we're searching a particular area, and we'll correct our count for the carcasses that fall beyond it. So we do need to know if that carcass is within the search plot. We need to know the distance of the carcass from the turbine. That will help us to estimate the fraction of carcasses within our search area. We need to know the carcass size, bat, small bird, medium bird, or large bird. Those are the important factors. And here they are gathered into a spreadsheet. So the spreadsheet on the right has data from 10 such forms on the left for the first 10 carcasses in this data set. And again, here's our carcass ID, turbine number, date found, size, and distance from turbine in meters. There's some other information in here. I've got a visibility class. This is one of those strata that I talked about, and visibility class might very well impact our ability to, our searcher efficiency values. So we need to keep track of the visibility for each carcass. Species and species group, that may be important for summarizing the data. It's not going to be critical to our analysis, but these are additional data you might collect. Carcass persistence. This again is the probability that a carcass remains in the search area until your searcher is able to come and look for it. And we will collect these data experimentally. So typically the process is to drop a series of fresh carcasses around the wind farm and then revisit them to check whether they've been removed. So we'll drop usually about 12 carcasses per season per size class. And then we'll come back and check them on days 1, 2, 3, 4, 10, 14, and 21 after we place them. And on each search date, we indicate whether or not the carcass is still available for a searcher. So the information we have here today, we've got a carcass ID code. We've got the season. Carcass persistence often varies by season. And here's the date and time that we placed that carcass. We placed it on April 12th at 11 a.m. We do like to keep track of the time. Our models will be more precise if we could keep track of the exact time. We need to know the carcass size class. Again, bat, small bird, medium bird, large bird. And then here are our check dates. We checked it on April 13, 14, and 15. On April 13 at 9 a.m., the carcass was intact and present. On April 14 at 12:10, the carcass, someone had chewed on it. It was scavenged, but it was still present. This data point is represented in red. It's actually this carcass right here. And there's our 2.05 days that have elapsed since we placed it on April 12th, and it's still present. And then we check it again the next day on, April 15th at 8:50 in the morning, and that carcass is absent. It's been removed. And there's our 2.91 days since we placed the carcass, and now it's gone. So this is what the data look like on the right that go into the analysis. We've got a carcass ID, size, season, the last time we know that carcass was present, and the first time we know that carcass was absent. And it survived somewhere between 2 and 3 days, but we don't know exactly how long. The software will take care of that we don't know part for us. The important part is that we have this last present and first absent record for every carcass. Searcher efficiency data, again, experimentally collected, and this is to estimate the probability that a carcass sees a carcass, a searcher sees a carcass, given that that carcass is available in the search area. Again, season is going to be important. Carcass size class. I should back up. The way these data are collected, we have somebody who's not the searcher, a trial administrator, goes out and places carcasses before the search. So usually on the morning before the search, they will place a number of carcasses that are marked. And the searchers are unaware of the timing or the location of these trials. So it's no good to tell your searcher when these trials are happening. Otherwise, they're perhaps more alert than they otherwise would be. When the searchers find the carcasses, because they're marked, they can report them. And then the trial administrator records which of the carcasses were found and which were not found. And with those data, we can estimate the probability that a searcher sees a carcass. So the data: season, size class, same as last time, bird, small bird, large bird, bat. The visibility class, this one shows easy, moderate, difficult, and very difficult. The data that we're going to use today will simply say, is it a road and pad, which again is a gravel prepared surface and easy to search, or is it a cleared plot, which with vegetation, which is somewhat harder to search. And then I have in yellow the things that you'll most likely see. We've got a search date, whether it was found, and then if it's not found, the trial administrator will go and ask, was it available? Because some of the carcasses that don't get found may have been removed by scavengers, and we we need to account for that. So carcass administrator needs to check for each carcass. Was it available to be found, or was it perhaps removed? Now in green, it shows attempt number 2, 3, and 4. There is a parameter that you can estimate using GenEst. It's called the detection reduction parameter. It's complicated. I can't get into it today, but generally what you do is you'll leave that carcass in the field for multiple searches. And if a searcher misses the carcass the first time, they may have the opportunity to find it the second or the third time. That's very expensive to do from a trial administration perspective, and it requires a very much larger sample size of carcasses. So we're not going to touch on that today, but just so you know, that's why these fields are here in the template data sheet from the Good Practice Handbook. And that's what these fields would be in carcass data if you're working with the example data set in GenEst. It's rare to see that anywhere in the world. I've estimated it maybe twice in my life. Finally, we have the density weighted proportion of area searched. One of the great unfortunate things about GenEst is that it cannot estimate the density weighted proportion of area searched. It cannot estimate that area correction for you. There are at least 4 ways to estimate DWP. A couple of them are available in packages for the R statistical computing software. They are really for advanced R users, people with some statistical background. One is called WindAC. That one was created by West. There's another one that was created by the USGS called DWP. Our tests show that they both work very well. But for people who don't have access to a statistician or the statistical computing skills, the simplest way to estimate the DWP is in Appendix D from that Good Practice Handbook. So the handbook has a relatively simple tool that will provide an estimate of the DWP for you. And I think at this point, I have to leave the comfort of my slides and move into the data. Just looking at the chat, I see there was a question, how do we mark carcasses to ensure that we're not double counting them during a repeated search? So that's a very good question. If you go out and you find a carcass this week, that carcass may persist until next week, and you want to make sure you're not counting it. In the United States, our searchers obtain permits from the U.S. Fish and Wildlife Service called salvage permits, and they're then allowed to pick those carcasses up. That's very convenient because if you pick up a fresh carcass, it can be used in one of those bias trials I talked about as searcher efficiency or as a carcass persistence carcass if it's fresh. If it's not fresh, we can still use it for searcher efficiency. In the event that we can't get that or don't get that permit, or if there's some reason, if it's a protected species, we usually aren't allowed to pick them up. If we have to leave the carcass in place, we use spray paint. We'll come with a can of spray paint and just put an orange slash over the bird so that we're not touching it, we're not interacting with it, but we've marked the carcass. Alternatives would be to take a good GPS location. That's might work as long as the scavenger doesn't move it in the interim. So, and I think we've also put weighted buckets over carcasses to kind of keep them in place and mark them. That's a little extreme and costly to do, but there are a number of ways that you can deal with preventing carcasses from being double counted. Now, back to my talk. I promised you a way to estimate the density weighted proportion of area searched. So this is an Excel spreadsheet with some data that is fake data, but data nonetheless, that look like the data you will need to be able to estimate the DWP, or density weighted proportion. And what we're going to do for each turbine, I have your turbine number 1 and turbine number 2. And here's a picture with the turbine at the center. And for each turbine, we're going to define a series of circular rings around the turbine. And those rings are going to be 5 meters wide. So 0 to 5, 5 to 10, and so forth. My data are from a plot that was searched out to 60 meters from the turbine. So I've got 12 of those. And my plot is in this picture on the right. Again, the turbine's at the center. The plot here is a square that's hatched. The plot that's represented in the data is not exactly a square, it's actually a circle. It's a 60-meter circle. And so the proportion of area searched within each one of those 60, with each one of those 5-meter rings is indicated there. So we searched 100% of all of those rings because it was a perfect circle. And that's information we're going to need to estimate the number of carcasses that fell into our search plot. On the right, we have a more extreme case. Again, this is where we have searched just the turbine pad and the access road. And this is turbine number 2 for a road and pad search. In this case, these are very much not to scale, so don't expect them to be to scale. But in our first 5-meter band, we searched all of the area. That's all on the turbine pad. Our second 5-meter band maybe started to get off that turbine pad, and we've got 80% of the area searched, and it drops off very rapidly, 70%, 10%, 8, all the way down to about 3% by the time we get out to 60 meters on this turbine number 2, because we're only searching the very narrow area compared to the entire circle around the turbine. So we need to know the fraction of area in each of those 5-meter bands. That's best accomplished with the GPS unit and then put into a GIS system to estimate. You take the GPS and you walk the search area, and you use a GIS then to estimate what was actually searched. If you don't have access to a GIS system, you can estimate it using graph paper, but you do need to get some kind of an estimate of what fraction of the area was searched. Same data. Here are my distance bands, 0 to 5 meters, 5 to 10, and so forth, out to 60. And across all of the turbines, what's the proportion of area searched? Now, here I haven't included that road and pad turbine, but I'll take an average at each 5-meter band across every single turbine that I searched for what the fraction is that was searched. And I will put the carcass count. So here across my entire wind farm, I had 3 bats within 5 meters of a turbine, 5 within 10 meters of it, or 5 to 10 meters of a turbine, and so on. I'll do that same process for large birds, same process for medium birds, same process for small birds. And now my data are formatted, and I will go to my appendix tool. This spreadsheet is the one you actually download from the IFC's website. This is the appendix to that good practice handbook. And it's a big, complicated spreadsheet. It's just the 2 that we're working with today are the turbine density weighted proportion. It will also estimate density weighted proportion for overhead lines if you're searching under a power line. And there's also a tool that will help you place searcher efficiency carcasses for your carcass trials. But today we're just looking at this density weighted proportion for turbines. There are instructions on the instruction sheet. And this is the actual worksheet that does the work for you. This is the same data I showed you before. We've got proportion of area searched for each of our turbines 1 through, I think there's 23 in this data set. And again, I've assumed that I've searched a perfect 60-meter circle around all of them. So I made my life easy. We searched a full fraction of all of the area around those turbines out to 60 meters and nothing beyond. And here again are my counts of carcasses for bats, small birds, medium birds, and large birds. So cells in blue, we're gonna enter data. Cells in yellow are various data checks. Those will go red if there's something wrong with the way you entered the data. And this is the output. This is the information we're actually after. This is the density weighted proportion of area searched. And this number here, this is small, so I apologize, 0.929, says that approximately 93% of the bats at turbine 1 will occur in areas that we've actually searched. That number is identical for all of my turbines, and the reason is that I searched 100% of all of my turbines. If I had searched a road and pad over here, we'd see that turbine 2 would have a somewhat different area correction. But in this case, each turbine's getting the same one because they're all perfect circles. That's the information for bats. Small birds, just 40% of the small birds occur within the searched area. Medium birds, 54%, 55%, and large birds, 73%. Large birds tend not to get blown by the wind, so they often have a tighter fall pattern. And now we've got all of the data formatted. Again, we can get to our GenS software on the internet by going to this web address, which is now in your chat and in the reading materials. I'm going to put this away and I'm going to do it locally on my computer because I don't want to trust the internet any more than I have to this morning. This is the R software instructions for how to start the software are in the user manual. You just have to run, you have to work with the code for just a minute. And then GenS will open up in a browser window. So whether you're using it on the internet or whether you're using it on your local machine, it still opens up in your web browser. This is a local to my machine address. It's talking to the statistical software on my computer. So this is GenS, version 1.4.9. And GenS is, I think, fairly easy to use as long as you understand that there are multiple layers of menus. So the menu at the top here it'll open to the help screen every time. And then there's a second menu below that has getting started. These are basic instructions. GenS ships with example data. There are, 6, 7 data sets here that you can load automatically, and you can look at how to analyze those. That's helpful to familiarize yourself with it. And the next 2 tabs are just, there we are, the people who put it together, and some disclaimers from USGS and West. Very importantly, here's the GenS user guide. If you click on that, it will download a PDF of the user guide, which is, again, I think a very helpful resource. It's included in the reading materials I gave you. We're going to go to data input, and we're going to need to load all of our data files. Now it expects these files as CSVs. So I've got those prepared. Searcher efficiency. I have a carcass ID, carcass size, season, visibility. That's actually whether it's on the road and pad plot or whether it's on a cleared plot, and whether it was found or not found. 0 for carcasses that we didn't find, 1 for carcasses that we did find. The carcass persistence data. Come on. Carcass ID, carcass size, season. Last present is the last time we saw that carcass, the last time that we know it was in the field. At time 0, that means that was when we dropped it, when we actually placed the carcass. And the first time that carcass was absent. So the first time we visited the carcass and we found that it was gone. These are decimal days. So 0.93 is something short of 24 hours, but close to it. 1.97, that's almost 2 days. Here's one that says int, that's infinite. That's a carcass that lasted longer than our trial. So usually these trials will last for 3 to 4 weeks, and then we stop with trying. And if the carcass survives that whole time, we write infinite, and the software will deal with that problem for us. We need a search schedule. Here are my turbine numbers in columns, turbine 8, 9, 10, and so forth. And the search date, this was a long time ago, 1955, in rows. And for each search date, I've indicated the season, and just simply whether that turbine was searched or not searched. So you can see a kind of a diagonal pattern here. We often don't search every turbine on the same day. We'll search some on Monday, some on Tuesday, and so forth. So the search schedule is fairly simple to compile, but it's critical. And then finally, carcass observations. So these are the dead things that we found. We've got a carcass ID for each, which turbine it was found at, the date, the visibility class, whether it was a rodent pad or a full plot, carcass size, large, small, bat, and distance in meters from the turbine. And those are going to be entered into our GenS software. Some of you may appreciate I have to slow down as I do this in real time. So I'll load the searcher efficiency data. I will load the carcass persistence data. Here's my carcass search schedule. Here is my density weighted proportion of area search data. And last but not least, the carcass observations. And then if you need to, you can look at those data sets by clicking on the menu items at the top here. So that's data input. For analyses, there are a couple of things that we set for the entire analysis. Number of iterations, you can almost always leave that at 1,000. The software uses a simulation process to generate confidence intervals around the estimate. And this number of iterations is just the number of bootstrap iterations that it uses to develop the estimate of confidence or the estimate of variance around our estimate. So 1,000 is almost always the right number. Bigger numbers will slow the software down. Smaller numbers, you might not get accurate estimates of variance. The confidence level, usually we report estimates with a confidence level. 0.9 is typical for wind wildlife research, so we'll leave that at 0.9. And then it needs to know which column in our data indicates the carcass class. In our case, it's size, and there's only one available. It kind of tries to guess. It looks at the data, and in this case, there's only one correct answer. So carcass size is always in a column called size. Now we'll get to the modeling. For searcher efficiency model, it needs to know model inputs. Again, it's going to try and guess from the structure of the data what your model inputs should be. S1 is the column name of the column that, there it is, S1. This indicates whether that carcass was detected or not detected. We've got a carcass size class, and this is simply a serial number for each carcass. The predictor variables, we're going to see if searcher efficiency differs by season. And we're going to see if searcher efficiency differs by visibility. And we sort of expect it will by visibility. I honestly don't know off the top of my head if season is going to be important in this data set or not, but we'll test it. This K value, again, is a detection reduction factor. I can't get into it today, but a good number to use if you don't have data is 0.67. That's a number that is very close to what I've estimated 2 or 3 times. And at least 2 additional researchers in the United States have come up with numbers close to 0.67 as a good estimate to use if you don't have your own data. One of those researchers is Manuela Huso of USGS, who's one of the leading wind wildlife experts in the world. So we're going to go with 0.67 since we don't have data to estimate it. We then run the model, and it will take us immediately to the model comparison menu. So there is our data, here's our model comparison. We need to choose the model, and it's looked at whether searcher efficiency can be modeled according to visibility, according to season and visibility. As a constant, that would be neither season nor visibility matters. The searcher efficiency is the same everywhere. And then is there an interaction term or is it just season? And these models are always ranked according to this AICC score. I can't get into AICC, but in general, a smaller score is better. AICC evaluates the goodness of fit. How well does your model fit your data? And it penalizes you for extra parameters, penalizes you for a more complicated model. So AICC kind of finds the sweet spot between a model that fits well but isn't too complicated. And for our purposes today, we'll just take the lowest valued AICC. The software, you can download this table. It'll download it as a CSV file, a spreadsheet, and that's useful for your reporting when you get to reporting. And this is a thing that should actually be in every report. You can also download figures that indicate what your searcher efficiency is across your different strata. You'll select at large birds, the searcher efficiency will be different, and so forth. So you can select all of your size classes, and there are a number of plots. And once again, these can be downloaded at the bottom of the screen for inclusion in your reports. The estimates, this is going to be the information that was in that plot. And it simply has the number of carcasses used to estimate that searcher efficiency, and here's the searcher efficiency itself. It's 0.636 for carcasses falling on cleared plots in the fall. What are we looking at? We're looking at large birds here. If we look at bats, we can see it's quite a bit lower. For plots, it didn't matter by season for bats, by the way, but on plots, the bat searcher efficiency was 0.358, and on the prepared road and pad surface, it was 0.567. Once again, you can and should download these tables for inclusion in your report, and you'll have to download one for each size class of carcasses. Finally, the model will not advance if you don't formally go to this model selection. This is that AICC score I mentioned. Small number is good. In each case, we're just going to choose the smallest one today. So I've selected a model for bats, large birds, medium birds, and small birds. I can download this again, and I should for my report. That's searcher efficiency modeling. Carcass persistence modeling. Model inputs, the structure is the same for these different models within the GenS software, so it starts to look a little familiar, I hope. But the model inputs for carcass persistence, when was the last time we knew that that carcass was still in the field? So that's the decimal date that is last present in our data. So this is just asking for a column name. Last present, in this case, it was when we dropped it. In this case, it was about a day after we dropped it. And when was the first time we know that that carcass was missing? So that happened in the first absent column. Finally, what are our predictor variables in this data set? Just season. We don't expect, sometimes we test whether different plot types have different carcass persistences. Carcasses may find, or scavengers may find it easier to find plots on, or carcasses on roads and pads compared to in the vegetation. But in this case, we're just going to test for season. This is a little in the weeds, a little bit technical, which distributions. And there are 4 of them that we typically test. It's a good idea just to test all of them and let the carcass, let the model selection sort out which one works best. We'll run the model. And here again is our model comparison table. Now there's a lot more models because for each of our models, whether it have a season or whether it doesn't have a covariate, there's going to be these 4 distributions: Weibull, log normal, log logistic, exponential. We don't really need to understand that. Again, the most important thing is this model selection metric, and today we're going to make it simple and just choose the smallest score, which is the best supported model in this case. We can download those, we should, and we can look at these model selection tables for each of our size classes. The software produces figures. These colorful lines are the different models. I think our best model here was a Weibel, and if 100% of the carcasses were available immediately after they fell, we've got time on the x-axis. We can see that as we move out to 5 days, it is about 70% of the carcasses are still available. That is, 30% of them have been removed by scavengers in 10 days and so forth. And so that's what these figures show. As always, they can be downloaded. And what we have is there's a difference by season in those carcass removal dynamics. And the differences in carcass size classes are selectable here. So we'll get one series of figures for each carcass size class. Again, bats are moved faster than, in this case, large birds, which persist quite a long time on the landscape. Estimates, same information as in the table. This is the median carcass persistence time in days. For large birds, that's 27 days with a 90% confidence interval of 22 to 32 days. We can download this table. This is the persistence probability. So these are going to be, R1 is the persistence probability for 1 day, 3 days, 7 days, 14 days. So these are all going to be numbers between 0 and 1. And based on your search interval, this is the probability that a carcass survives until a searcher is able to come and look for it. Once again, you can't proceed without doing the model selection step. We're going to select the AIC value of 0 for each of our bat, large, medium, and small bird size classes. And we can download this information for the report. Finally, we're ready to get what we're after, which is the mortality estimate. So how many things actually died at this wind farm during the study period? It needs to know the carcass identification column. In this case, it's carc ID. It needs to know what fraction of the facility we searched. I'm going to assume today that we actually only searched half of the turbines. So if we had a 24 turbine wind farm, we might have searched 12 of them. And it needs to know which column indicates the date found. And then this will take it a minute. Whoops, apparently I did not finish doing model selection for medium birds, and it complained about that. So we'll try again. It'll take it a minute to estimate mortality. And when it gets it, it's always an uncomfortable moment while you're waiting for the machine, hoping it hasn't crashed. This is the estimate of total mortality at our facility, and it's a distribution. We don't know exactly how many. As I said, there's a simulation process, and it tries to get bounds on what might have happened there. And this is the distribution of what might have happened. Somewhere between 400 and looks like maybe 1,100 things died. And the median estimate, this is our point estimate. If somebody asks you how many died, you'll say, well, 713 and a third. So that's your best point estimate, and we've got confidence intervals. Now, those of you who know anything about wind wildlife work will recognize that this number is a little silly. We don't usually want to know how many things died. We want to know how many bats died, and we want to know how many large birds died, and we want to know how many small birds died. So this is the everything, but we're interested in splitting that up by carcass size. So this area down here will split your estimate into different classes. I'd like to know by size. I can do by carcass ID. That's a little silly. It'll give you an carcass picked up. You can do it by turbine. That usually gets a little bit excessive also, because you get a separate estimate for each turbine, and things start to get a little imprecise when you make that many different estimates. You can do it by visibility class. I don't know why you'd want to, but you can. Distance, basically anything in your carcass observation table, but usually there's a very small number of things that make sense. So also, we're often interested in fatality estimates by season. You can have two variables in the search schedule, so two time-based variables, and I can't remember probably just 2 on the carcass observations table too, but I don't remember what the limit is on that. Now we're going to split that estimate, and this is useful information. Estimated fatality on the Y scale and season on the X scale, and in each panel, here are the bats. We have a few of them dying in spring, not very many in summer, and a large number in fall. This looks like this wind farm is in an area where there are not that many resident bats, but they seem to be migrating through. Large birds, biggest risk seems to be spring for whatever reason. Maybe it's a migratory path corridor. There do seem to be some resident and fall birds that are killed at this facility. Medium birds, more or less constant across the 3 seasons that we sampled, and small birds, there's a very, very strong seasonal pattern with most of these killed in the spring. Right now, the scales are different on the y-axis for these different sizes, but we can ask it to put it on a common scale, and then we can see that, wow, mostly bats. That's what we're going to be concerned with. It's the same numbers, I've just adjusted these Y scales. So more bats than anything else are perishing at this wind farm. That's not uncommon. Small birds are the next most common. Large birds are actually quite rare here, but large birds are often more sensitive in terms of their biology. These again are figures that you can download for your report. And in the summary tab, the top, same information, but it's just in tabular format. So bats in the spring, here's our point estimate, a little bit over 11 bats, and the 90% confidence interval will be the 5th and the 95th quantile, so 11. I'm a little baffled why we're getting 56. Oh, excuse me, 11 is the count. I'm sorry. That's the raw count that your searchers found in the field. Here's your point estimate, 108 bats approximately, with a 90% confidence interval of 56 to 95. I was a little alarmed by what my software was doing for me there. So this table, again, you will almost certainly want to download and include it in your report. GenEst has one more feature. It's a detection probability estimator. So you get your data, you want to do a little better next year, you want a higher detection probability, and you can simply tell it, well, I plan to search every 5 days, and this is a study that's going to go for 200 days, and it'll estimate what your detection probability will be. As your detection probability increases, you get better precision. That is, your confidence intervals become narrower and you're more certain of your estimates. So this is a feature that may or may not be interesting to you. But here we see if we search every 5 days on cleared plots that may have some vegetation on them in the fall for bats, our detection probability is going to be about a third. We'll find 1 bat for every 3 that dies. For large birds, I hope it's higher. Yeah, we'll find about 8 bats for every 10, or excuse me, 8 large birds for every 10 that dies at our facility. So just about an hour. We've got a few minutes for questions if you should have them.
Paul, thank you very much. That's fantastic, and I think it's really useful. I had to leave and then come back. I can't see if there are questions in the chat, but if people have questions, please either write them in the chat or raise your virtual hand, and Yen-Leet can unmute you. And I think Paul is happy to answer questions.
Right now, I'm not seeing any questions in the chat. Paul, did you feel that you fully answered the question about double counting? Or is there, oh, there is one new message popping in here.
There's Jill, there's also a person with his hand raised.
Okay, so the question we have, somebody missed the part about the 0.67 estimate. And could you get back on that? Maybe repeat that or explain that a little bit more.
Yes, I can. That's a difficult parameter. And that is the parameter that I think when I showed you a slide that had the simplified equation here, that 0.67 is a parameter that's not on this slide. It's called the detection reduction factor. It's also called K, and that is the one that's actually responsible for making the real equation much more complicated than this. What it does is it says if you miss a carcass when it's fresh, on the first search after it arrives, you probably will have a lower searcher efficiency for that carcass if it persists to a second search. So the reason is, if you miss it once, there's probably a reason you missed it. Where is it hiding? Is it under a bush? So on the first search, you find those that are intrinsically easy to find. On subsequent searches, you find those that were maybe more difficult. So we expect the searcher efficiency to be lower. The other thing is that carcass might be disintegrating through time. So usually, this is terrible presentation practice, but because I didn't intend to do this, but I've got a little toy here that tells you what the detection reduction factor does. If your searcher efficiency is 0.8 on the first search here, and your searcher efficiency is let's make it 0.67 like I suggested, 0.67, that means that on the next search, it'll be a little bit over 0.5, your searcher efficiency, and on the next search, your searcher efficiency will be, looks like about 0.37 to me. So every time you miss a carcass, that searcher efficiency is reduced by this factor. So if it's 0.67 and your initial searcher efficiency, I'm going to change the numbers on you, but to make it easy for myself, if it was 0.6, on the second search, it'll be 2/3 of that, or about 0.4. On the third search, it'll be 2/3 of 0.4, and there's the math I can't do in my head. But that is what that detection reduction factor is. We almost never estimate it in the United States. It's expensive. I've seen it estimated, again, by Manuela Huso for carcasses from the northeastern US. She got a value of 0.67. I've estimated it for carcasses in Illinois, Indiana in the US, and I got numbers between 0.67 and 0.8. And another gentleman, Dr. Skalski, estimated it in Iowa, and he also got numbers of about 0.7. So this 0.67 is a good value to use from what we can tell. The other good news, your fatality estimate is actually usually not very sensitive to K. If carcass persistence times are very, very long and your searcher efficiency is very low, then K becomes important. But in most cases, the estimate doesn't vary much with K. I see somebody's hand up.
Right. Ofer Steinitz has a question. He's been waiting for a while. So, Ofer, can you go ahead?
Yeah. Thank you very much for the wonderful talk, and also thank you for this powerful tool. Really useful. I have two questions. One regarding the K. Is it also this 0.67? Is it also valid for dogs, or and the second question is that I noticed that the estimates of the carcass persistence and the figs and your the estimates and the figures are not the same. If you look on the carcass persistence and you go to the figures, the estimate is not the same as what is shown in the figure. So what is the relations between them, and what is the correct estimate?
The median estimate here, that's a very good question. we're looking at an exponential distribution right now.
Mhm.
And this estimate is the parameter for this exponential distribution. R1 and R3 and R7, the persistence probability for these time intervals, these should match the figures. I certainly hope they do. So large carcass class exponential with no covariates, large exponential, no covariates. And we should be seeing, I forget what my 1 day, 3 days, 7 days. So 1 day is going to be very close to 0.97, 3 days, a little closer to 0.9 and so forth. So these values, the R values, should match what's in the figures. This is the parameter. For an exponential distribution, this parameter happens to be approximately the average removal time for that carcass. So if it lasts 27 days, that means that after 1 day, there's a 99, 98, 99% probability it's still there.
Yeah, I played a little bit with your example, and also in other examples, I noticed it doesn't match. Maybe we'll see it in when it goes down, but maybe I'll show you the example directly.
Yeah, if you'd like to send me screenshots, I'll be happy to look
Yeah.
at them and try and interpret. There's a lot going on here. One is to make sure that your carcass class and your distribution and your two parameters are the same for the figure and the estimate. And the other is you might not necessarily want to see all of the distributions. So make sure you're looking at the same distribution. And then I hope that we'll find the figure and the estimates for the R values similar. Your second question was, do dogs have a similar K value to humans?
Mm-hmm.
John Skalski estimated K for dogs. It was not the same as for humans, but it was, I can't even remember how close it was. But here's the issue with K again. This, I'll put this in the chat, if I can find the chat. This app that you're looking at, again, this is available on West's website. And it kind of will let you play with K and see what K does to your estimates. So what we're looking at now is just a thing that kind of explains how K works. But what does K do to your fatality estimate? So it asks you for your search interval, mean removal time, searcher efficiency, K, which right now is 0.65, and area correction and so forth. With those parameters, if your K value is 0, every carcass will be translated to 9.5 carcasses. So for every 1 bat you pick up, your estimate goes up by 9.4. If your K value is 1.0, every bat represents about 4 carcasses. And you can, as searcher efficiency gets higher, you'll see the sensitivity of your estimate to K goes down a lot. If your K is 0, your estimate's 3.14. If it's 1.0, your estimate's 2.22. So it doesn't matter if your searcher efficiency gets high. It does not very much matter what K is. You get roughly the same estimate. Additionally, if your removal time is short, and for bats, 8 days is not a bad estimate, short removal times also reduce the sensitivity of your estimate to K. So here I'm plotting the sensitivity into searcher efficiency and mean removal time. And you can see that as removal time gets short towards the bottom of the graph, and as searcher efficiency gets high towards the right, there's very low sensitivity over here. So yes, they're different. They're also different for large birds than for bats. But luckily, in those cases where they're really hard to estimate, it tends to be that it doesn't matter very much. So we use 0.67 because it's simply so expensive to estimate what K is.
Okay, Paul, do you want Ofer to respond to that? You do have one other comment in chat.
Is there a program or course that I can take to become a certified specialist? Unfortunately, there is not a set program that you can take to become a certified specialist. USGS and West did offer some workshops on Gen S when it was first released in, I think that was 2018. Manuela Huso has since retired, and I don't know that any workshops are planned. Really, the best thing you can do is to work through the user manual and work with those examples. Like I said, there's about 6 or 7 example data sets. So it's going to be a teach yourself kind of a thing. At this point, I don't know of any training programs that are available.
Are there other questions from the audience? Well, if there are no other questions, yeah, please raise your hand or write questions, and feel free to write questions in Russian if that is better for you. Yenlik or Alyona can translate them. And if there are no questions, I think it would be really, I'm so pleased that Paul was able to talk to us about detection probabilities in Gen S. It's, he and Manuela and the others involved in this have built a software interface that's easy to use and can really make a big difference for estimating fatality rates. So I would encourage everybody to try it, to use it, ask questions. Jill and I can either answer questions or point you towards people who can answer them. So we're happy to do that. And other than that, I think we should thank Paul, maybe digitally, with applause. And we will have the next lecture in our series will be on January 9th, and it will be Tabor Allison who will be speaking about mitigation and some alternatives for how to do mitigation for take of wildlife. So thank you all very much for attending, and we look forward to seeing you in about a month. So take care.
I echo Todd's thanks, and I did put Todd and my email address in the chat in case you have non-Gen S questions, just more general questions. Always feel free to reach out to myself or Todd. Thank you.
Paul, I thought you did a great job. Your cadence was